Okay, class, we had talked on resistance. We said resistance is a holdback force, force of impedance. We gave the formula 8 nu L power to the fourth. We showed how you could add up resistances. We spoke of resistors in series, just like this, in a straight line, versus resistors in parallel. We said resistors in series, when you wanted to get the total resistance, summation, you would just add up the resistors of the various different areas as they change in radius. Resistors in parallel would be the reciprocal value. These are parallel. We said resistors in parallel get less total resistance, like this here. Less total resistance, less total holdback. Okay, so that was our generic. Now we come to calculating total peripheral resistance. But in this case, we're going to call it systemic vascular resistance. Systemic vascular resistance. Okay, so we're looking at systemic vascular resistance. All right, now what do we mean by that? We come in and we said, I'll show you here, that we had what we call the systemic circulation. The systemic circulation. This was an example of the systemic circulation going from the aorta all the way back to the venous system. That's the systemic. So what we're attempting to do is calculate the total resistance in this whole loop. Now that's about 56,000 miles of blood vessels in our body, and that's 70 kilograms. But that's what we mean by systemic vascular resistance. That's SVR. We can even calculate pulmonary vascular resistance. This is the resistance in the pulmonary circulation. So when I go back and I say TPR, SVR, I'm speaking of systemic vascular resistance. Now, we could do total peripheral, total pulmonary resistance. Okay? But in this case, we're doing systemic vascular resistance. So we would add up all the resistors in series and in parallel to come up with a number. And the biggest contributor to this, remember, is that radius. Okay? So we would add some up as this and some up as that as we use this. Now again, remember, this is a generic issue here. This is a generic issue. Okay? So when you hear me say SVR, systemic vascular resistance, envision that what I'm speaking of is adding all the resistors up in the systemic circulation. Okay? So we're setting the stage for everything. All right. So now we go to something else. Another formula of importance, diffusion. Now we talked about diffusion in ANP1, but here's the formula. This is called fixed diffusion equation. Now I just want you to kind of get an idea of this when we talk about it. Okay. Diffusion, which is the net movement of certain particles, we learned that in ANP1. But the force of diffusion, or how fast something diffuses, equals to the area that is diffused through. Now you see, this is in the numerator. A is the area. So the larger the area, shouldn't be take a great genius, the larger the area, the more room you have, the better the diffusion. Now this is called the diffusion coefficient right here. I'm not going to talk about that right now. We'll do that in respiratory. So this formula come back up. Remember, these formulas are for gases and liquids. We talk about blood, but gases work by. Okay. Divided by the thickness times, I'll come here, times CO minus CI. That's the concentration difference. Put N here. Let me go here, put an M. Times the concentration difference. CO concentration outside minus concentration inside is the concentration difference. This would be over 1. That 2 is in the numerator. So in other words, the bigger the concentration difference, remember from high to low, the larger the area, and the better this DC, which we haven't talked about. So for you right now, the more the area and the larger the concentration difference, the faster you can diffuse. The larger the area, the better the concentration difference. Now check this out. Look at that right there. That's a lot of area. See, that's why capillaries are exchange vessels, because they have a considerable amount of area. And they are thin. When we get to them, they are thin. See, that's thickness right here. That T is thickness. That's in the denominator. The thicker something is, the less the diffusion. Okay, so I want you to keep that in mind. All right, so that's diffusion. Go into another deal. Capacitance. Remember we said that the veins were the capacitance vessels. What we said was, let's look at that. What we said was, is that most of the blood, let's blow this up, most of the blood is in the veins. They have greater capacitance. Most of the blood's in the veins. Okay, what is capacitance? This same formula is for compliance. Compliance is stretchability. Well, let's think what I mean when I say compliance, then we'll get to capacitance. So you're sitting there with a leather pouch and a balloon. You're sitting there with a leather pouch and a balloon, and you're going to blow both up. When you get ready to blow into the leather pouch, since the walls are so stiff, it takes a lot of pressure to blow that leather pouch up. Probably won't be able to blow it up. But if you take the balloon, it's more stretchable. So therefore, a little bit of pressure can blow it up significantly. Compliance. So compliance equals to change in volume over change in pressure. How much volume change do you get for your pressure? How much volume change? See, that balloon, a little bit of change in pressure blew up the volume a lot. But that leather pouch took a lot of pressure change. So that meant the balloon had better compliance. But capacitance the same thing. A little bit of pressure, big change in volume. A little bit of pressure. We said our veins were the capacitance vessels. We just saw that the veins are holding more of the blood. Well, why are they capacitance? Why are they our capacitance vessels? Let's look at this. Look there. The veins stretch out easier than the arteries. The veins stretch out easier than the arteries. Okay, so you can quite naturally see that this would be our capacitant vessels. Okay, so that's that. We go now to another concept, laminar flow versus turbulent flow. We talked about this a little bit with murmurs in the heart, I did. Laminar flow, sometimes known as streamline, occurs when a flow flows in parallel layers with no disruption between the layers. So the layers just kind of slide over one another. Look at this picture. See how they kind of slide over one another. In turbulent flow, though, something causes them to bounce into one another. It may be a constriction or something. It may be a constriction. But that turbulent flow makes a noise, and that turbulent flow has more resistance to it. So there are two flow patterns for gases and liquids: a more smooth laminar flow and a turbulent flow. Okay. That turbulent flow, when we get ready to study how to take blood pressure using a stethoscope, we have to convert laminar flow to turbulent, because laminar flow is quiet. You can't hear it. So with the blood pressure cuff, and you'll be hearing me, we'll have a little talk on that, you're converting that to a turbulent flow. Okay. So turbulent flow versus that. I won't get into the Reynolds number. Okay. I won't get into the Reynolds number. All right. So now we're going to do one more thing, but I'm going to close this out here.